I know it pretty well. I learned how to do lab books. I'm super good at it. Anybody can learn this stuff. The rules aren't hard. You have to be disciplined. For your lab books, single best advice ever. Fill them out in real time completely. Nobody writes half a prescription and then comes back to fill it out later. That's crazy. Do it in real time. Do it while you're doing it. Period. You're filling out an order to buy something online. Do you stop halfway through and come back a week later? I don't think so. Graham, are you playing on your phone? Come on. I don't even work here. All right. I'm going to see if I can find some notes to share with you guys. Okay. Yes, Dr. Zed has joined us. Nice. All right, you guys. So, we've kind of caught up to where I wanted to be earlier, which is hilarious. Let me remind you, if you have questions, ask me. You're not interrupting. I'm not going to get mad. I'm already like halfway cranky or crazy anyway. But if you don't know, please tell me, and I'll try to explain things the way, right? If you don't say anything, I'm going to assume you got it. I mean, there's just no way for me to know. So please, well, Carla, I'm looking at you. Try not to be so critical of my, addiction to plaid. I mean, it's personal choice, right?
It's a good look.
It's all good. Did you folks notice it was raining yesterday? Like out of the sky?
Yep.
Yeah.
I was thinking, it's all over. Here we go. Here comes summer. And then I got up this morning, went out with a dog, and I go, oh, well, winter's still here. Forget it. So, not quite yet. Alrighty. So we're going to be looking at some very basic principles. So they're not only valuable for the exact stuff I'm going to talk about, the exact science. There's going to be examples, particularly in the reactivity, that will apply to a much broader range of chemicals. So every time you look at a reaction, try to remember, we're looking at a specific example, right? But we're also looking for the trends and the behaviors of these chemicals. Because honestly, they almost all behave the same way for the same reasons. Short version, positive things are going to stick to negative things, vice versa. It is not rocket science. Half the battle, where are the functional areas, that is the areas of denser electronegativity. That's also how you name it. And secondly, please count the carbons. Even I could do that. Dr. Salazar, is that making sense? Or you're wondering, I know your first question. Is this going to take long today? Yeah, I'm thinking I should go to like 4:15. No, I better not. Bavic's already stroking his beard. It's getting ugly. Okay. So you can see this, I assume. Aldehydes and ketones. You guys all took biochemistry, the intro part? Are you taking it soon? You know biochemistry? Really well?
We're taking it now.
Okay. Well, the two fundamental main groups of sugars that are in you, that you consume, etc., are aldoses and ketoses. Aldehyde sugars and ketone sugars. And here's what they look like. Aldehyde, RCO, H. Ketones, RCO, R. That structure in you, in your metabolism, in your cell membranes, in your cell cytosol, oodles of these things. They are a normal, functional part of your structure. They are unbelievably common in every living thing, except for those nasty little viruses that I find extremely annoying. Ribose, for example, in DNA, oxyribose nucleic acids, or RNA, it looks like this. But here's a little secret about these things in real life. Although in organic chemistry, people like to draw them vertically, and you can basically say, the hydroxyls go to the right, here you go. The truth is, if you put a sugar in liquid, it always forms a ring structure. It reaches around and it grabs its own tail, and they exist in a circle or cyclic form. That's why when we draw DNA together and genetic molecules later on in advanced biochemistry, which you're doing with me, you're going to see right away that they only exist as a straight conceptual diagram on paper. They exist in circles. They also often have distinctive odors. When a scientist says to you, the odor was distinct, or that smell was memorable, that can mean it was really great and memorable, but it usually means it is pungent. It might even be acerbic. Small ketones can actually be sort of sweet. Often fruit flavors are based on ketones. The common denominator in these carbonyl compounds, that's the word to remember, folks, CARBONYL, carbonyl compounds, is the carbonyl structure. They have that carbon that's slightly positive, and they have that oxygen that's slightly negative. It is always trying to pull electronegativity towards itself. Therefore, by fundamental definition and the basic properties of physical chemistry, this oxygen is ever so slightly more negative. This carbon in the carbonyl structure is always ever so slightly more positive. And that will always tell you, you know where things are going to attack. Negative nucleophiles will attack the positive carbon. Positive electrophiles will attack that slightly negative oxygen. It's not like you have to guess, right? It's just there. Read them and weep. Little table of some of my favorites. Formic acid. If you were asked to make ether to pull out the king's teeth in the year 1531 because you're an alchemist, I don't know if you know how law works in the 15th century. If you do something wrong, they don't throw you in prison. They torture you to death. So you're pretty motivated to be a good chemist. You would probably take a whole bunch of red ants, boil them down to get the formic acid, and use that with alcohol to make a very crude form of ether. Don't go around torturing red ants, by the way. Red River College does not endorse ant torture. Get a herring? I can see you're thinking of it, but don't do that. All right. Acetic acid, you know glacial acetic acid, 1% from vinegar. Propionic acid, butyric acid, zoic acid. They're different structures, different carbons. All of them, without fail, are RCO and then an H on the end. Where do we make these from? They're made out of carboxylic acids, and I will cover that later in detail. If we were in the lab, you'd be having the great time doing what I call the ester lab. After students have done the ester lab rim, they all refer to it as the stench lab. Why? It's a classic example of what happens in organic chemistry. The conditions that will form your target molecule, a certain carboxylic acid, will also revert back. And what happens is, in your boiling reflux, you've got the molecules flashing back and forth between two structures into a sort of equilibrium. And the best you can hope for is a partial yield, which is pretty realistic. Although most people think if they're going to make a nice fruity banana smell, it's going to smell like bananas. It will. It'll smell like bananas and burning and death. It is extremely unusual that you will do a reaction that'll have 100% completion. It's rare. Okie dokie. Terminology. You need to know that the carbonyl carbon is always the carbon attached to the oxygen. It is having its electrons pulled. It is the most positive carbon in this structure. Here's the deal. Because it's having its electrons pulled, it's turning to its neighbor and stealing cupcakes off the table. I got to just let some more folks in here for some reason. Give me a second. It's going to work. Ay, ay, ay. Okay.
Thank you.
Just let me get these people in here. Okay. That'd be the whole rabbit time thing. Pain to stop. Where was I? Oh, yeah. So the oxygen is pulling electrons. It's making the carbonyl carbon ever so slightly positive. Well, what it's doing is, because it's deficient in electrons, it is pulling slightly on the carbon next to it. Not as strong as the oxygen, a little bit. And because this is called the alpha carbon, it is one carbon away from the carbonyl carbon. If you go 2 carbons away, it is called the beta carbon. It is being pulled on too, but a little bit less. So oxygen is pulling for electrons hard on the carbonyl carbon, but is pulling on the next neighbors, the alpha, the beta, etc., a little bit, but always a little bit less. What that means is when you look at a molecular entity, things that are close to, we would say proximal, things that are close to this charge group are all affected. The further away you are, the less the effect. It's going to get rid of that. Questions or thoughts?
David,
If there-
so the carbon from the carbonyl group, the one attached to the oxygen, that's the carbon number 1, right?
But I mean, we refer to it as a carbonyl carbon. Just, that is the definition. And the first carbon adjacent to it is always called the alpha, and then the one that's 2 away is always called the beta. You can go further, but the electron pull is so weak the further you go. Again, closer you are to loud, rude neighbors like my house, the noisier it's going to be. And it's just basically the way it works. So I did want to talk very, very briefly, just so it's in your book somewhere, on how we synthesize these things. I have a love-hate relationship with these because the way people tend to do this in industry is with some fairly nasty materials. And no matter how you try to do it, you're going to wind up with some contaminants that, as an environmental chemist, I just don't like. So the reaction is called Friedel-Crafts. Friedel-Crafts. It will involve aluminum or a lithium aluminum compound. I'm sure you're well aware that aluminum has been implicated in Parkinson's and a number of diseases of the central nervous system. I'm not a big fan. And the reactions aren't necessarily as easy as you think. For example, in this first example, we've got a primary alcohol, ROH. We're using CrO3. That's chromic acid. Chromic acid dissolves things on contact. Chromic acid is in the murder movie on TV when they want to get rid of bodies. This is not something I would ask you to work with in the lab casually. It's also why you need to be in the habit of looking up those MSDSs, because some people will not think twice about having you, the technician, work with this. You have to be aware. It's in pyridine, and what do? We're oxidizing it. The Friedel-Crafts, and again, I am not a fan of working with powdered aluminum. When you go to weigh it out, you're going to be breathing some in. It is not a good idea. That lithium aluminum, it's in water, it's a protic environment, you're stripping away this chlorine, and yes, technically you're making an alcohol or an alkyl halide, you're making your aldehyde or ketone. It's just not very clean chemistry. I'll give you lots of examples of how to do these things in better ways further in. Ketones, we've got chromic acid again. We're stripping away our hydrogens. There we go. And this one is so dangerous, I only threw it in to show you things you need to be aware of. Why would I hate this? I know what you're thinking, Andrew. Because it's organic? Yes, partially true, but not what I'm looking for.
That's a nitrile? No, an alkyne, sorry.
No. What is Hg? You guys don't know the periodic table? I'm going to have
Mercury.
Mercury.
Mercury. Yeah. Methylmercury implicated in teratogenic effects, all kinds of birth defects. The methylmercury is found in the Bay of Tokyo into all the fish, into the ecosystem. It is a proven mutagen. It has huge teratogenic, that is embryonic mutations and effects. Bad mojo. So telling you to go work with mercury and heat it up is not something I'm going to do. When you read a reaction, a lot of people just read them and go, well, this is where the reaction is. That's true. I'm always looking to think, how much unreacted mercury are you about to pour down the drain? Part of the responsibility of being in science and organic chemistry or designing industrial processes is that you're doing it as cleanly as possible. Folks are going to want it as cheap, as economical as possible, but you sort of have to marry the two, make it work financially. Please don't go throwing a lot of mercury down the drain. Bad stuff. Aluminum chloride, Friedel-Crafts type reaction, and we're adding on a different R group. Basically, it's just a taxi cab. These are really here, not for you to memorize, but I wanted you to see that I can pretty much make anything out of anything. I cannot always do that in a clean and professional manner. Many of these are low yields. In terms of formaldehyde, this is only just for comparison. Strangely, formaldehyde wants to form. The only thing you have to do is slightly heat. Formalin, paraformaldehyde, trioxane, there's a whole families of compounds. Every single one of them will decompose and make formaldehyde, or as we call it, methanal. No one ever calls it that anymore. Easy peasy to form. The trick in organic chemistry is not to get reactions to happen. It's much easier than you think. In fact, even without heating it, even without adding protons and making it a protic environment, very, very often it's already starting to react. Getting it to react to a particular endpoint and stop, that's not so easy. Most of these engineering processes I've been involved with, we did a reaction where we try to transfer something to make a product, but then we have to figure out a way to harvest that product and somehow limit all the toxic other stuff that gets formed. Nothing is formed in isolation. And that is a big takeaway, hopefully, from today's lecture. Now, this is very basic concepts for aldehydes and ketones reactivity. I've touched upon it before. Are you listening? You need to know this. This is a huge metaphor and example for how and why things react. So, addition reactions, I talked about it before, we're kind of reviewing. Really, one of two things is happening. We've got our R groups, we've got the oxygen trying to steal electrons. Every one of these carbonyl compounds is physically going to do a similar thing. The positive electrophiles are attracted to the negative electrons around the oxygen, and nucleophiles are going to be attracted to the relatively positive carbon. Read them and weep, that's how it works. Now, general points, and again, I'm talking about aldehydes and ketones. This applies to many more structures than just those. Many reactions, number one, involve protonation, adding a proton to the carbonyl oxygen. What happens is, temporarily, in a transition state, a proton comes in here, and we've temporarily lost a bond here. This is going to want to become stable. It also means down here, this carbon, for a brief instant, is completely missing a bond. How many bonds does carbon want?
4.
Did you say James? It wants James bonds? Cute, but wrong. You're right. 4 is correct. So when this happens, even if it's only for a nanosecond, this carbon becomes seriously positive. Any nucleophiles near it, they're in. It's happened. It's already happened before you turn around. It also means, this is so positive, that a relatively small negative charge, we would say a relatively weak nucleophile, can now react. And that is why in organic chemistry, so many reactions involve adding acid. It is a strategic destabilization of certain bonds. It's not an accident. It's on purpose. If it's a carbonyl carbon or structure, you add protons, this is going to happen. You will form that carbocation, and that will inevitably lead one of those one mechanisms. The amount of reactivity, that is how complete a reaction is, how fast it is, how big is the boom, relates to the amount of positive charge. Bigger charge, bigger collision. More complete reaction, very simple. The bigger the positive charge on this carbon, the greater the reactivity. Many of the things we will be doing in organic chemistry are variations of how do we make this charge stick out? How do we exaggerate it? How do we make it so it happens at the right spot at the right time? Bigger charge, bigger reaction. It is not complicated. Things that tend to stop this, if you've got a big charge, but the molecule stretches from here to Portage la Prairie, effectively, it dilutes the significance of that charge. The more things that are attached, the greater of a distribution of that instability over the whole compound. You following me? Stop following me. I'll have you arrested. All right. So the bigger the molecule, the greater of a distribution of that instability. It's not 100% like it won't react. It's just comparatively, you're smoothing it out. So formaldehyde, lowly hydrogens, virtually no protection here. It's going to be as reactive as it could possibly be. If you do an R group on one side, two things are happening. This R group is beginning to help share those electrons. It's reducing reactivity. And finally, you get a ketone. You've got two entire attached groups. They're helping to soothe that instability. And simultaneously, that whole steric interference is occurring. To react with this, you can basically attack it from anywhere. It's just open. Here, this R group is blocking your access. So you're going to have to drive all the way around to the liquor store over by Walmart. Maybe not that. It's just my example. Down here, it can only be attacked on one side physically at all. So you've got two things going on. A distribution of charge that makes it more stable and less reactive. But you've also got steric or physical interference. Steric hindrance means, to react, you got to collide. But if you got to drive all around to find an available parking spot, the reaction slows down. These factors affect everything. You have to get the things to collide at the reaction site. Questions or thoughts? Not a big idea. It's an important idea. You can also have specialty groups. We would say functional groups or priority groups. Basically, when you look at them, in one form or another, they all tend to be electron withdrawing groups. They all tend to be electron hogs. What do? They destabilize. Just like the oxygen in a carbonyl group is pulling electrons, these are big charges, big negative charges. They're pulling on electrons on whoever they're attached to. So they are creating additional localized areas of instability. For my money, a bunch of carbons and hydrogens is relatively inert. The places where it's different with respect to charge and electronegativity is where the reactions are going to happen, which is why knowing how to name them is basically telling you exactly where the reactions are. If it says 1-chloro something something, I already know where it's going to react before I see the rest of the name. Anissa, you joined us. Thought you were late. What's that? You were? I know. I'm so unfair. You don't actually have to attend lectures. You do have to attend labs. That's how that works. All right. Just to break it out, steric hindrance is a term you do need to be able to explain, both verbally and with text. It's an important concept. More stable structures, we know, are less reactive, but the bulky groups also cause physical interference. And I wrote right here, you have less or reduced access to the reaction area, in this case to the carbonyl group. This little tiny guy, relatively good access. If we stick a great big group attached on one side, well, now wow, this is very hard to get in here. You've got about 1/4 of the access. And what you find is the reaction rate and the extent to which a reaction will complete, whether it's 50% or 100%, is greatly reduced. Physically, you can get in here, but if you start tacking on great big groups, there is not much access, and reactivity will plummet. Examples. Little aldehyde. Well, there's only a hydrogen on this end, and that means it's pretty easy to get in here. Easily, Bavik, the most reactive. No question. You add a methyl group. Well, it's harder. It's not impossible, but now you do have to go around this. You make it an ethyl group, it's a big drive to the other side of the parking lot, and it's just going to be more difficult. The reaction will slow down, and it may proceed to a more limited completion. So you guys okay on those concepts? All of those count. Protonation is one of the number one ways that we start off a reaction. It makes a bond in a carbonyl structure, temporarily a hydrogen, and makes a very transitory carbonyl cation right here. That cation is the source of nucleophilic attack, the main target. And when you look at many, many reactions in organic chemistry, acidification is usually one of the steps. Just saying. Degree of reactivity, how big is the charges? How big are those charge discrepancies? Big charge, big reaction. More completion, typically a faster rate. Electron withdrawing groups, cause their own flavor of trouble by doing what? Well, Brooke, they're withdrawing electrons. That's right in the name. They withdraw electrons, it's going to make something else in the molecule more positive and provide another site of attack. It's almost uncanny get reactions to happen randomly in just a chain of carbon. It's almost always going to occur where one of these priority groups is. So again, the rules that name it are telling you where it is and what's going to happen. And finally, since they have to collide, steric hindrance means it's physically hard to get in here. There's 4 things sticking out of space. It's tough to get in the reaction site. That will slow things down. Guys, okay? Suffering nicely? What's that? You wish you were in communications playing on your phone? Whoa, Sarlene, that's harsh. Wow, okay, fine. Tough crowd today. Addition reactions. So I'm going to give you some examples and introduce a couple terms that may be useful later. Addition reactions involve, are you ready for this? Adding things. Seriously, in organic chemistry, like they're literally in the question giving you the answer. It always blows my mind. I'll go through an answer key with someone, they go, wow, the answer was the question. They go, yeah, it was. It literally said it. Things, and there's many, but I'm going to give you a few examples. Water, super common on Earth. Not only is it a good leaving group, it's also a good reacting group. Alcohols, yep, alcohols work great. Cyanides, unfortunately, cyanides are highly charged, chemically very sticky molecules. They are more than willing to interact with your hemoglobin. They are more than willing to interact with any opposite charges, and they are extremely effective at that. And finally, Grignards. I'll show you those in a minute. A Grignard is basically a commercial molecular Uber driver. You buy a Grignard reagent, and they will tack on the chemical you want to do in a reaction. They literally make this for you, and all you have to do is mix it together. So a Grignard is something you buy. You typically don't prepare it, and you'll say, I want to have an ethyl group I want to add. And they say, okay, here it is, give us money. And you just buy it and use it. So reactions with water, when you add water, you're doing a complex reaction called, Dr. Beckett, are you listening? Hydration. When you lose water, the reaction is called, don't say hydration, don't say hydration. Holly, don't say, is it dehydration or hydration? You're losing water.
Dehydration. Dehydration.
Isn't that what happens to humans?
Yeah.
It's literally exactly that. There's no thinking here. If you add water, you're making ready a hydrate. Dr. Henderson, you're familiar with a hydrate? It has multiple heads. You cut one off, it grows more. No, that's a hydra. Never mind. Different thing. I'm assuming you guys didn't study Greek mythology? You're very lucky I'm not teaching communications. We'd be doing a lot more languages. All right. So when you add water, you're making a hydrate. Here's the new term. If you look, H2O, so here's the structure. You're adding an OH on one side and a hydrogen on the other. You've made a diol. This has 1, 2 alcohols. It is a diol, and it has its own term. It's called a hydrate, yes, because you added water, but it's called a gem diol or a germinal diol because it's on the carbonyl carbon. It means the reaction that you did happened on carbonyl carbon. So hydrate is formed any reaction where you're adding water. A gem diol is when it happens specifically on that carbonyl carbon. They're both, it's both a reaction making a hydrate. It's just one has a certain term, which you may be seeing later. So I thought I'd warn you. If you add water, you're doing hydration. If you do hydration, your product is a hydrate. You've added H2O. Carlo, is that making sense? Look, here's your water. Add a proton here and stick the OH over here. This carbon has 4 bonds and nobody gets hurt. What's that? I can't teach organic chemistry like a mafioso guy? Tough crowd today. Okay. Example. Acetone, Guys familiar with acetone? Yes? No?
Nail polish remover?
Or
Yeah.
in Victorian England, you would smell it on the breath of diabetics who are untreated, which is bad. And I'll go into the physiology of that much later in advanced biochemistry. But you do make acetone as part of your normal pathways, but you make it in really trace quantities that don't affect your overall cellular health. All right, acetone, nail polish remover. Add water. What are we doing? Split the water in two. One of the hydrogens goes here, and the remaining hydroxyl goes on the other side. And slang here would be acetone. This is the easy naming. Hydrate, which is typically what most people will call it because they're lazy. Or you could name it 1, 2, 3. So it's 1, 2, 3. Methyl, ethyl, wethyl. It is wethyl, isn't it?
Prop.
Propyl.
Right. Is that your final answer? Do you want to call a friend or use a lifeline? No, you're good with that? Okay, fine. So propyl, but I know it's a propyl diol, except I have to use numbers to tell you that it's on carbonyl or second carbon. 2 propane diol, I'd take 2,2 propyl diol, I'd take propane 2,2 diol, all because when I go to draw that, it makes the same structure. The only warning I would give you is in some analytical chemistry labs, they're going to want the IUPAC name only. But just be aware, almost all of these are going to have multiple acceptable names. Generally, these things are seriously chemically reactive. And why should that not surprise you? You got an oxygen sitting here pulling electrons. You got an oxygen here pulling electrons. Very short version. The more discrepancies of charge in a molecular entity, the far greater chance of reactions. You got 2 electronegative centers, ready? You got 2 times the electron pull. Rem, is that making sense? It doesn't make sense. If you have 2 oxygens, you have 2 times the electron pull of 1 oxygen. If you have 3 oxygens, how much more electron pull do you have? Guess
3 times.
Yeah. If you have a gillion, which isn't actually a word, you will have a gillion more pull. It is literally a quantification of the number of these electronegative centers. More charge distribution you have, greater the reactivity and potential for reactivity.
Can I ask a question?
Go nuts.
Doesn't the oxygen cancel out their reactivity, the electron sharing, because they are not next to each other?
Yeah, it is not polar. I think what you're saying doesn't the polarity changes the dipole moment, but it doesn't change the fact that this is electronegative. Like it doesn't cancel it out. It cancels it out in terms of overall polarity and interacting in a solvent. That's a different thing. It's quite true, but it's a different thing. This is still negative. This is still negative. They're both susceptible to a positive thing coming in. Okay. I'm bringing this in here because in biochemistry, we're going to talk about this. And the word you need to know is hemi. Are any of you familiar with the word hemi? Aren't you going to insert a joke about a Hemi engine that you bought was very expensive and nobody understood why? All it means, ready, in this case, it means semi or partially. I don't know why they don't call it semi, but they call it Hemi. So let me explain. If you add 1 alcohol to something, to an aldehyde or ketone, it is called, and this is a particular term I've put in quotes and I've underlined in red. It's going to come up. Hemi-acetyl. And I'll show you with a diagram. If you attach 2 of these groups, it makes a fully acetyl group and you lose water. So let me show you. First thing you need to observe here isn't the chemicals. The first thing you need to observe here is these arrows go in both directions. That says to me immediately that you're not going to make just one thing and have the reaction stop conveniently. But like most of these, it's going to be in some kind of flux and reach a chemical equilibrium. We will attempt to manipulate that equilibrium with a variety of conditions. look here, this is an aldehyde, RCOH. To it, we're adding an alcohol. What's happening is this alcohol, R prime OH, is being split just like water, H2O. So the R group is attaching to this negative oxygen, you can see it here, and the remaining hydroxyl is coming underneath and attacking the positive carbon. However, the conditions that destabilize this will mean the reaction keeps happening. If it keeps happening, then our group can now attack this other oxygen, and you end up with two OR groups attached, and you've made water. This is considered an acetyl compound. This is considered a hemiacetal compound. I'm not going to go nuts with this stuff. I'm just saying you're going to see this again in advanced biochemistry. It has metabolic significance, so we're not going to be able to get away from it. Okay, so I'm not going to freak out and do a bunch of tricks with this. Just be aware. If you've added the one OR group, it's a hemiacetal. If you add the two, it is fully acetyl. And you may notice, as you start to work with more and more chemical names in the lab, you're going to see acetyl so-and-so. So this will come up in ever-increasing amounts as we proceed. Reactions with cyanides are so simple and easy to do. They're outrageously... Don't cry, Rim. I could do this for like 6 hours in a row. Hydrogen cyanide. Can I give you a real-world example? My old buddy, who I used to share an office with, Dr. Green, was a mathematical genius. I mean that. Very funny guy. Served, was conscripted into the Vietnamese War by the Americans. He lived in Oregon as a kid, and at 17, they drafted him into the Air Force. When he got back from the Vietnam War, he was discharged. They had promised they were going to pay for his school. He kissed his mother, drove to Vancouver, and stayed in Canada the rest of his life. And I asked him, why would you do that? And he said, because they made me kill people I wasn't even angry at. I will never, ever go back. And he never did. He was a superb mathematical genius, and he was also extremely good at the quality system stuff I've been talking to you about. He was hired by General Motors, the company, you might have heard of them, as an outside professional auditor and quality advisor. And one time he got a call, middle of the night, in Winnipeg, from one of their main plants. I'll leave the locations and everything, the specifics out. A whole bunch of people in the lab had dropped dead, and they wanted him to come down and investigate. So he gets down there, and they had looked at the bodies, and they all had blue lips and blue skin. And he immediately goes, well, they're all cyanogenic, it's obvious. And they tested here, they tested all the room, they couldn't figure it out. He went onto the roof, and he looked at the physical layout, and he realized that the fresh air intake that allowed air to come in so that your, the vents you're using to remove the toxic gas are actually pulling it out successfully. With a certain direction of wind, the cyanate gas, the hydrogen cyanide, was going up and then blowing sideways over the roof and drawn right back into the room. And they were all dead. So they obviously instituted a bunch of changes. I don't think that ever made the press, for example. But the reality is this stuff is that toxic, and you're largely asymptomatic until you have real symptoms. Just saying. So if you have to work with cyanates, any capacity, appreciate what you're working with. If you have to work with a cyanate gas, it's a life-threatening circumstance, no more, no less. Just saying. Boy, am I ever mean today. Yeah, but, I kind of have to warn you about these things. It's not a joke. So when you've got cyanates, you're going to have a cyanate ion. It is super reactive. It is a hulking, large, negative charge. We have a carbonyl structure. Slightly negative oxygen, slightly positive carbon. This negative charge here is so strong, it will slam into here instantly. This is one of those reactions that will happen impossibly fast and is really, really hard to stop once it goes on. The worst part, it is incredibly useful in organic synthesis. Therefore, many of those train tanker cars that stop you when you're waiting in Winnipeg for that stupid train to go by, if you're able to see it slow enough to read the labels, They ship around all sorts of cyanohydrins because they are so useful in industry. If one of those tanker cars goes over and opened up, say goodbye to the water system around there. It is a seriously dangerous material. A cyanohydrin, cyanate on one side, CN, and a hydroxyl group on the other end. This is a reaction waiting to happen. Therefore, it is useful because you can drag along any R group, any alkyl group you want. So, of course, it's favored. It's not expensive. It's cheap. It works well. It's also incredibly toxic. Try not to, in a lab where they don't test events. Didn't I ask you guys this week if you'd seen the calibration units on the flow hoods? You guys all checked those calibrations, right? The flow hoods you use in the lab? Yeah, they're on the back side by the wall. You might want to check to see that you're using gear that works. Saying, because I've seen the consequences. So as a consequence of that information, Dr. Green had us put all those monitors that we could guarantee at any point in time, anything in that lab, in that flow hood is gone. Just saying, kind of good to know. Cyanohydrides convert to carboxyls or esters. They're super reactive. This is only from biochem. I want to show you just how close to being a lethal machine you actually are. This is not for you to memorize. This is for a point of weird chemical interest. Aldehydes acting with sodium cyanide and ammonium chloride. It makes a cyanohydride. It keeps reacting and eventually makes the amino acid alanine. Great. What's the catch? Oh yeah, it makes 60% amino acid alanine. That means 40% is typically unreacted stuff, like sodium cyanate. Any reaction where you're using these materials will have some of the materials left over and react. If you've got a good plan, you can harvest them and sell them or use them some other way, but they don't go down the sink. Boy, am I ever mean. All right. How many of you have been to South America? Seriously? Oh. Manuel, of course. So listen, did you wander into the rainforest for some reason?
Yes, in Colombia.
Sweet. So here's the deal, and I don't know if you've seen these. Typically in the rainforest, if you see something that's fluorescent orange or fluorescent yellow, that is nature saying, walk away. Right? In Canada, it would be like a 600-pound biker or something like that, or maybe a tiger running loose. But in the rainforest, little tiny frog this big, fluorescent orange, it is not a cane toad. Don't lick it. The example I want to give you is from, ready? Aphaloria or Ugata. It is a millipede. It's about that long. It's pretty big. It is orange. It's got black legs. It moves quick. What can it do? It has a compound that we're not quite sure of the structure with enzymes we do not comprehend. What does it do? Inside of its own body, in real time, it converts benzaldehyde, makes benzaldehyde, and squirts hydrogen cyanide and kills anything attacking it. So over the years, creatures that like to pick up bright orange millipedes and centipedes and eat them are all dead. Dr. Beckett, if you're in the rainforest and you're hungry, just like go to 7-Eleven, get a hoagie or something. Don't eat bugs there. It's just not good business. Did you guys know this? Dr. Manuel, did you know that? Bright orange, don't eat it. Yeah. All righty. This is just a quick summary of a commercial reaction that occurs. You buy these. You don't make them. There's nothing to do. You would go online. You go to the Sigma Aldrich catalog. You buy them. So what it allows you to do is to add things. A Grignard reagent is something you buy to add certain chemicals. Rem, stop yawning. I'll jump into the screen. All right. I'll wake you up there. Is that helping? No? Okay, fine. It makes a magnesium alkoxide and you pull it away. Here's the reaction. You see this? Here's the whole deal. RMG. You buy this. You buy it, though, is for a particular R group. Do you need to add an ethyl group? Do you want to add something 16 carbons long? You literally look it up and say, I want you to make this. I need to buy that for reaction. It is basically a commercial transaction on an industrial scale. What happens is, if you just look at the end of it, here's our RMGX. We've got RCOH. What does it do? It's going to add an R group, and it's going to add the OH. So basically, this is a vehicle to add specific alkyl groups. There's no finesse in this. You buy it and you mix them together. It is the simplest thing you could do. It is a commercial reaction. In this case, I've made a secondary alcohol on this tiny aldehyde. Simple, easy peasy. So what I want to show you is, and I'm not sure if it's going to pertain to you because your exams are online, but I want you to get the basic similarity between the way these things work. So I slapped them together here. Let me show you something. Aldehyde or ketone, I don't care which. RCOR or RCOH. If you add water, where's the business end of this molecule? Holly, I'm like literally touching.
Hydrate.
Yeah. What do you get? You've hydration.
Yep.
You've added water.
Hydrate.
Where's the business end? If you add alcohol, where's the business end of this molecule? Sorry, just practicing. It's the same spot. Oh yeah, it's exactly the same spot. If you add cyanates, where's it going to react?
Same spot.
Yeah. Is there anything to figure out? No.
No.
What's negative and what's positive? You could use Grignard reagent, RMGX. What are you adding? Very expensive R group. Where you'll see these are people making difficult to make compounds, things that you can't actually do casually or easily. None of these are terribly hard. They're always in the same space. The thing you need to remember generally, folks, is that there's no surprise where the reactions happen. We write R, it means an alkyl group, carbons and hydrogens attached. But when I look at them, the only place I can see is, here's the reaction site. I already know positive things are attacking here. I already know negative things are going to attack this positive carbon. It's going to happen that way all of the time. Questions or thoughts? Gio, I know what you're thinking. You're already on Amazon trying to order Aphiloria corrugata. They will not sell or transport poisonous, murderous little centipedes over the Canadian border. Although I'm connected with the zoology department at U of M. We'll talk off screen. Yeah. Alrighty. Are you guys okay? Can I continue a little more, please? Is that okay? Organic is hard to take in large doses. I don't like to go more than an hour. You're being polite and you're disciplined. It's not easy to listen to. I get it. Let me just help you here. Addition elimination is ready. Add something. Here's the tricky part. Anissa, you following? Eliminate something else. It's literally in the damn name. So, look. RCOR. What kind of structure is that? Is that an ether?
Yes.
Is it cyanate?
It's ketone.
Ketone.
Oh, okay, I'll go with that. Sure. So the negative part of a nucleophile is going to come over here. And here's the secret sauce. There's an unstable intermediate. Organic chemists seem to go crazy imagining what that looks like. Allow me to say it's a theoretical, often logical guess. But because this is a transitory thing that exists for nanoseconds, it's not like you can go and measure it with an HPLC. So I'm not a big fan of making students memorize intermediates. They're an intermediate, which means transitory, and they exist for almost no time. So what happens? The nucleophile wants to attack here. End of the day. I'm going to do this for you. See this? You know what this is? Here's the oxygen right here. Look. Snip. And then the nucleophile takes over. Finished. Snip. Nucleophile takes over. Add it. Eliminate something. Oh, by the way, water formed. Did I ever tell you water is a good leaving group? Water, Dr. Kong, is an excellent leaving group. So if it can form, it will. In fact, I've seen people resolve fairly complex organic reactions simply by going, what's the easiest way to make water out of this? And it always works. All right. I'll just do a little bit more. You've been extremely patient. I want to talk about ammonia and primary amines because could you tell me what the number one product of Manitoba is? What's our biggest business?
Wheat and like grain.
Grains? Yeah, farming. I was going to say crime, but your answer is way better. Yes. By a huge margin, we produce outrageous quantities of foods. It's a short growing season, but because Manitoba is the bottom of a 10,000-year-old lake, it is seriously fertile soil. Here's the catch. To keep the soils fertile, we no longer do crop rotation, where every third year we would let it grow, with a legume, something like clover, to refertilize the soil. Instead, we drive a truck and we spray ammonia and hydrous ammonia and things like that all over the field. The catch is ammonia will react with things. Ammonia will get into the aquifers and the well water, and it can cause a condition called blue baby syndrome, which is just about as funny as it sounds. It's not funny. So, what happens? Ammonia is more than content to react with things in the soil or with chemicals in your beaker. What do we have? We've got RCOH, got an aldehyde. It's a protic environment. And what are we doing? We're doing a SNP, and we've added this. New term, underlined in red with quotes. That is a carbon double bound to a nitrogen. It is called, make sure you notice, an imine. It is unstable. If this happens in the soil, it's created conditions for all sorts of other reactions completely out of your control. It's not a great idea. So what do we do? SNP and stick. That carbon double bound to nitrogen is an imine. Unstable. Something I need to introduce as well is called a Schiff base. And the reason it's important is it really has a high reaction rate. This is benzaldehyde. We have a benzene sharing electrons, RCOH. We're adding aniline with a single ammonium group. It's a protic environment. We're losing water, and we've done a SNP. Substituted imine, just under 80%, 87% yield. That is phenomenal in organic chemistry. Almost impossible to achieve. It's a very stable, consistent reaction. I am not going to waste your time with a complex mechanism, but the thing you need to take away today is, look, add and then eliminate, or snip. Now, don't draw scissors on the exam. I've literally had people write add and snip and draw scissors. Actually, I gave them the marks because it was a clever way of doing it. So, snip and stick. You guys good with that? All right. So I don't want to do that structure. Just, you know what? I'm going to stop there. I think I'm pushing your rational envelope. Are you okay if I stop now? Or do you like more? Let's vote. Who wants more? I'm seeing everybody's hands are up. What's that? They're not? Yeah, here's the deal. It's a lot to soak up. I get that, okay? You've been more than patient. You have no other classes this afternoon?
No.
I see. I believe Geo is hosting a barbecue. Geo, are you hosting a barbecue? I'm not hearing a response.
No, I'm not.
All right, you guys. I won't be talking to you till, I guess, next week for our labs. And I believe I'm going to be doing buffers and titrations next week. You guys have already done titrations, right? So you're experts, huh? I'm going to go into the chemistry behind what you did. Remember, a titration is pouring accurately something into something else. However, pouring is the physical act. The actual chemistry is what you need to understand, all right? Is this your last class then of the week? Are you totally free now?
Yes.
There's a lab on Friday, like
Oh,
in
yeah.
person.
In person.
What are you doing in the lab?
It's microbiology.
Basic staining.
So,
Yeah.
so it's like a COVID transmission lab?
Yeah.
Shut up, Dave.
We're dealing with yeast.
Friday, yeah, Saccharomyces cerevisiae. It can make bread, beer. There's nothing that yeast can't do. My research group on Friday is working on the BA2 variant of Omicron. Yeah, there's a lot of stuff going on out there. We also have noticed that a whole bunch of places are planning to end the mask mandates. Allow me to explain. I hear people say, I'm so sick, I'm so over COVID. Allow me to say this, yeah? I'm so over gravity. Gravity, you can't tell me what to do. That's not how it works. Just saying, medically, you can't yell at a disease and tell it to stop. However, we are closer to the end. I'll talk to you next week, folks. Have a lovely weekend. Try to avoid doing crimes. And apparently, Gio is a little slow sending out those invites. Take care, you guys.
Thank you.